Welcome to the 30-minute case study webinar series. This is John Sankey. I'm an engineer for True Blue Technologies. It's a firm that represents or facilitates technologies from ASTIS, Tersis, TRS Group, and West Bay Instruments. So this series is a case study presentation group that focuses on the main topic of managing complex sites with high resolution characterization and focused remediation. So today we're really pleased to have Dr. Todd Hallahan ask and solve where are the contaminants going, scan to see flowpaths. Todd is a professor and Sun Chair of Hydrogeology at Oklahoma State University and serves as the Chief Technical Officer for ASTIS. As one of the recent NGWA McElhaney lecturers, Todd gave talks all over the world. And so Todd, thank you for presenting this presentation and case studies today. You now have the lead.
Thanks, John. And I'm always required to tell, and sometimes I forget to say it, but I've got two lives as a professor and as a chief technical officer. And so if you got questions about that managed conflict of interest, just let me know. And if you want to become a student, that's fine. If you want to become a customer, that's fine. It's just the rules a little different in each side of the shop. Thanks for joining us. And we try to keep these under 30 minutes so that people can get a little bit of information, but not be on Zoom until they fall over, these sorts of things. So we'll be respectful of that. So we're going to run about 20 minutes and then Q&A to follow. The little orange button, you can submit your questions and feel free to stick around and ask as many questions as you like. This is being recorded and you'll get a CEU certificate. And then we'll give away a prize of a Starbucks card or an Amazon.com card, depending on what kind you like. And that'll be, if you send questions, you get additional entries into the pot to try to win. So people tend to enjoy that. So here we go on the technical side. So when people take a class trying to learn about groundwater systems, they learn about hydraulics and some of the early stuff, thinking about how wells are functioning and how drawdown curves are working, but thinking about how paths would get to that well and thinking about how these systems are functioning, we do that with very, very little information. And so we work on theory, but when you come up with field data against that, if we try to build a flow net of a simple system dividing a couple of streams, and in this case, you've got 6 wells and a couple of streams. So you've got 6 to 8 data points that you're going to try to figure out how this flow system's working. And that's with horizontal and vertical movement. And most people have trouble catching both, especially when you've only got a half dozen wells. And that doesn't count for data quality, where the water levels might actually be wrong in one or more of those wells, depending on what's going on. So it's pretty tricky to actually build these. We can conceptualize them, you can read them in a book, but seeing them in the field, we don't typically have technologies that do very well with that, with using wells. So if we try to use an electrical technique and look around in the subsurface, now we can, instead of going from 6 to 8 data points, this is a simple karst system that you've got 22,000 data points that you use to figure out where did gasoline go in this case. And what that's going to allow you to do is to be able to look around at different flow directions. And in this case, the pink is where the gasoline came out of the tank. And then excuse me. Whoa, just a second. Then it came out and flowed down into a doline in the subsurface and went down to the regional water table. So having enough data to be able to see those sorts of things is how electrical can work. But we're going to look at how that works relative to trying to understand flow lines. But one thing I got to mention ahead of time is, in terms of taking images and understanding the subsurface, it gives you a picture of what's happening down there, the same way as a piece of chemistry gives you a picture of what's happening at one point, or a water level or something. But it's tying it with the other data that really tell you what's going on. And so the procedure that you need to go through is the same as a guy would go through if you're going to take pictures of somebody's liver and figure out whether there's a tumor, and if there is a tumor, is it cancerous? You got to get multiple lines of evidence and sort that out. But the scan shows you where to go at if you need to go after the liver. So that procedure is the same to do groundwater, and just having the picture does not tell you everything. It tells you what you think you have, and then you biopsy the tumor. So when you go to look for a flow line, there's a number of different ways to do that electrically, and this is single image thing of we're going to look at the subsurface, figure out where it's more conductive, more resistive, and understand what we have in the subsurface to deal with. And so if we have salinity moving, that's going to be a conductive fluid moving through the subsurface. So we can go catch that conductor moving and see if we can capture where it's at in the subsurface, look at it in 2D or 3D, and then understand where that flow line is and understand what it's doing to the flow system. If you're in a salty media where you've got a brine or a saline fluid, then you're actually going to be looking at a resistor of fresh water coming through. And so you could do it either way. It's harder to see a resistor than it is to see a conductor, but you can think about salinity, and that's sort of the easy one to think about. Lithologic flow lines are a little bit trickier, not too bad, but we're going to break the rock, and that break is going to cause it to become much more electrically conductive. And what will also happen is we'll oftentimes form a colony of microbes on there, but it's hard to tell as to whether it's just broken or whether it's also got some microbes making it a little more conductive. But we can look at where the rock's broken and pick off targets for flow paths. And then biologically, we can have microbes in the subsurface make it more electrically conductive and then watch where they're going. And a lot of times we think they're adding a little bit different surface tension through microbial biosurfactants. And that's going to be really key if you're looking at contaminated sites, of thinking about where biology is causing the flow to light up because they're living along a flow path. So the basic salinity one. So this is building a flow net. So you put some wells in a saline wetland in Nebraska, and the problem they have is their salinity is going down. And that's sort of weird. Most places are worried about salinity going up somewhere, but this is actually, the critters are based on a particular salinity, and it's freshening up on them. And what they had was that the stream incised by about 6 meters, and now the salinity doesn't appear to be coming up to the wetlands in that brown area. It just comes up near the river. And so they wanted to understand what was going on in the subsurface. So you could put in the wells and look at the salinities, try to understand the hydraulic conductivity of that location, and try to build a conceptual model. And you can tell that the salinity varies, but in terms of where is it flowing to, it's not real easy to pick out with that kind of data set. But we can look at it electrically, and this is the same wetland looking at electrically, and we can see that the most conductive things all head to the stream bed. They don't head to the wetland on the left. So the wetland is actually getting more resistive over time as it's freshening, and the source of the salinity, which should be coming from groundwater, is actually all coming out of the stream. Once it incised, it changed the boundary condition. And so you can think about modeling it, you can think about collecting data with wells, but the picture supports where things are really happening. And it also sees things that you go, hey, why did it get less conductive as we got towards the creek? And you're looking at hyporeic zone, and we've looked at several of these groundwater, surface water kind of flow systems, and you always have the image change right when you get up near the creek, because you're going to have the hyporeic zone start mixing down the water. And so it's mixing with the fresh water in the creek, and that's causing the salinity to drop. And so when you read these, it's showing you a picture where things are more conductive, more resistive, but knowing what it says takes a bit to think about what the flow system is doing versus what the picture is telling you about where things are at in the subsurface. This is a mound spring in a saline mudflat down by Lake Eyre. So this is all below sea level, and you have these mound springs come out that if you walk up that grassy mound in the distance, the further you walk up, the muddier it gets until you get to the very top, and then it's mushy like a marsh. It's fairly counterintuitive, but that's the way it functions. So that thing is spitting out fresher water, and it comes down and goes around, but trying to understand how they're plumbed in the subsurface, they come out as a series of springs. If you look at the aerial photograph, there's a set of them that come out, and trying to understand how they're connected in the subsurface, because it's all shale that it's coming through. So it's not something people typically think of as a highly permeable setting. But if we look at it electrically, we did some work to see if you could see resistive material coming through a conductor, because that's people tell you that, hey, you can't see something underneath a really bright conductor. And so that gray area is incredibly conductive salt water, but we can see the resistive material coming up in 2D or 3D and think about where those springs are at and how those fault blocks are interacting. And tends to be fault intersections that bring up this material. But you can understand how it's plumbed in the subsurface and work with the confining units and do all the hydrogeology you normally do, but you can see a bit about how that system is structured in 3D instead of just being able to have a well. And in these cases, these mound springs are all protected, and it's actually illegal to drill on them. So the way to look there is to look electrically and get an understanding of what's happening in the system by getting that kind of view, because you're not allowed to actually put a well in. And then if you're dealing with wells and you can install them, you can think about upconing and those sorts of problems. And we've got the problems in Oklahoma where there people are putting in a lot of wells into districts and they're starting to get upconing issues because there's saline water at depth. And then the freshwater aquifer, they go, hey, I don't have enough flow, I should go deeper. And they go down and they catch the interface and pull it up. But in terms of proving that, it's quite difficult. But if you take an image, we could look for, instead of a salinity measurement coming up, we can look for conductiveness coming up. And so this is a well where that occurred. And so we can look at this conductor comes up and up cones into the well screen, and we can have some indication that, yeah, it's an upconing problem. In Oklahoma, we're worried that it could also be oil field salinities from the shallow pits and things. And so you can demonstrate that, no, it came from the bottom, it didn't come from the top. And so even though you've only got one well with one chemistry in it, you can tell which direction it came from and have an understanding of the process. If we go to lithologic ones, you're standing in this photo on a granite chunk of the outback, and you're looking across an old telegraph station to the Great Artesian Basin. So a set of sandstones there in the background. And you're looking across about where that telegraph station is. It was built on a set of springs that's along a main regional fault between the granite and the sandstones. And if we look at that spring, the spring's a little bit fresher than it should be based on being a Great Artesian Basin spring. And if you look at it, you get the Great Artesian Basin, the GAB fluids are coming out of that sandstone in a couple different beds. But you also get the Peak and Denison Range granites fluids are coming up to that spring as well. And it makes it about 10% fresher than it would normally be. And so you can detect that that's coming out a little fresher, and there's also some other places to get even fresher water on that granitic side. But watching a flow net electrically, you can actually see that structure. And if you start to think about how many wells it would take me to drill to understand that structure, it's a lot of drilling. And in this case, these another one of these springs that's illegal to drill into to understand what's going on in detail. And it would just be incredibly expensive in the middle of nowhere. But this kind of system, you can actually watch flow nets develop and see how they're functioning. When we look at springs in these things, almost never does the spring align up to the top of the flow paths. It always kicks over at the very end in the top 30 feet or so. And this is about a 300-foot deep image. So when you start looking at these things and you're looking for a spring, if you drill in the spring, these data sets say wrong place to drill, you got to take the image and figure out which way you need to go from there to actually see it. The other thing you got to think about with lithologic targets is apparent dip issues, and we're going perpendicular to the fault, but we've got to think about where the fault is at, and if we don't know where it's at, that makes it trickier thinking about what the apparent dip of features is when you take a 2D figure. Another lithologic location, this is a 3,000-foot dolomite aquifer in a rural area that needs water. And the problem they have is that they've poked a bunch of holes in different parts of the aquifer, and some parts are very prolific, some parts are not. And this is a part that isn't. There's no map faults in this area, and the attempts at putting in wells, they've gone down hundreds of feet and they get like 10 to 20 gallons a minute. So trying to get a rural water district well in there is quite difficult. But going in and taking images, this is a little bit bigger than a kilometer, and we did imaging from the surface down to about 700 feet in this setting. But we targeted this fault, and it was based on knowing what the aquifer looks like, and we'd had so much imaging in this aquifer that we know what the electrical pictures tell us, and we can understand what we're looking at. Even though there wasn't any map faults, we could find the faults and fractures in here and see which ones are major, which ones are minor, and also look at the questions people have when they're trying to do a drilling target about, hey, can I get that water from that point to somewhere useful? And so integrating all that into data sets and picking it, we could pick out a spot, they drilled it, and instead of getting 10, 20 gallons a minute, they got 450 gallons a minute. So they got enough for a rural water supply. And that kind of approach, it's interesting to me because there's a cost to taking the images, but drilling multiple holes to hundreds of feet, yeah, that cost us 100,000, and we only did it 3 times. And it's wait a minute, you don't want to be spending that kind of money. Take a picture first and drill 1 hole. But it's a funny social thing about whether people want to take the X-ray or just go in for surgery. Microbial ones are a little weird, and microbes, the longer I've dealt with them in the subsurface and groundwater, the weirder they get. And Harvard already figured that out, that even if you take them into the lab and treat them nicely, they do whatever they damn well please. So on the left, you've got one carbon source that got all moldy. On the right, you got a carbon source that won't get moldy. And we have some notions of why with food, but in the subsurface, we have some notions, and it's sometimes good, sometimes bad. So you get the feel of it. So if you got a chunk of moldy cheese, you know that you can cut off the outsides and get to something decent in the middle if you're still hungry. And the same thing in the subsurface, we're starting to get the handle of patterns of these guys in the subsurface and things we expect to see with the patterns, but they still do things that I'm not sure what they're doing. But in this case, we're going to look at a microbial line going to surface water body, and this fits the pattern for every surface water body problem we've looked at where you have an apple coming out on a water body. So in this case, you've got a long seep at the edge, but you have a site that's been under regulatory cleanup orders for about 100 years. And so there's material to be found, the red dots, basically anywhere on the site. And yet you're supposed to stop stuff from coming into the stream and pick a spot to do that without trying to clean up the whole thing, because it's still an active rail yard. So in terms of looking at that, we could do an electrical scan across the site. And so here's a number of images across the site that they could use to figure out things for planning on the site and understand the flow processes. And there's resistors there that are incredibly thick remnant hydrocarbons. And so the system near the stream, you can sample it with a spoon, and it's really thick stuff. And they were trying to figure out, how is that getting through our system and popping out at the stream? This stuff, you can't even sample it. How are you gonna actually have it flow underneath and pop out in the stream? So when we look at the conductive side, we find there was actually another source that was incredibly conductive, and we found that it was microbially active. And you drill along there, and they drilled 6 holes along the line, and each one of them had mobile NAPL. And so you can get an understanding of, hey, we're looking for a conceptual model of going to the water body that is controlled by where the microbes are feeding and doing their things, and the elevation is changing, and it's based on how they're growing and interacting with the contaminants, not just contaminant movement on its own on an inorganic process. And so those flow lines are interesting because they have a growth component, and they have really bizarre chemistry along them because you're doing all those kind of bioreactions along the way. So in terms of things we've learned, you can use these images to go figure out what the flow system is doing. You could do that on like a gas station site, but you could also do it on an aquifer basis. And we've done it in, as you know, kind of scale of 3-4 kilometers on a side by 700 to 1,000 feet. So you can get into aquifer scale imaging and think about that, or you can do, hey, I got to clean up this gas station. Trying to do these kinds of images with wells and trying to put together a data set that you can see that flow system process, it's not going to be clear. You might get the data to tell you it's going up or down, or it's going left or right, but you're not going to get that kind of complete picture. But on the other hand, if you got the survey data and you need to prove something on a regulatory basis, you go, electrical data supporting this, but we're still going to want to biopsy and demonstrate that the concentration at that location is what we were worried about or trying to manage, or that we want to find that water source for a good flow path for water supply. So in the future, as we move forward from here, that was a lot of single images of looking at what the structure is right now. And doing that involves thinking about where you're going to take the images to deal with which way the flow direction is going. And what you want to try to do is be perpendicular to flow, because you get the widest possible chance of catching a flow path. So if you're looking at stuff coming out of a landfill or something, you go along the edges of the landfill and catch it in the image, you can see where the path goes. But then you got to know how to read the image and figure out where to put a couple images so you can demonstrate the path orientation. And working that out is sort of a different way of thinking than where you're going to set a drill rig. When you look at the same aquifer over time, and so for example, that Oklahoma aquifer we've imaged for a long time now, we now can take images and interpret them incredibly quickly because we know what its picture looks like. Similar to if I took the first X-ray ever of a human abdomen, I might know something, but I'd be fairly confused. But if I took the 10,000th one, much more sure I'm going to understand what I'm looking at. So that's happening in a number of aquifers where we're getting enough data that we can do more work, but it also tells us that kind of procedure works, that the more you take the pictures of the aquifer, the more you understand how to utilize those data if that's the most efficiently. And then we've been doing a lot more work now to image sites over time temporally. And so you take 2 electrical pictures and you see what changed. And the rocks don't change, but the groundwater moves and that changes. And so that we've got a segmented horizontal well that we've installed that we're now monitoring. And then we've got a aquifer with the largest spring in Oklahoma that we're now going to be monitoring over time and watching the seasonal changes and watching how the spring responds to storm events and those sorts of things. So that data over time is the same as being able to watch water level over time, except for you're going to look at 2,500 water level measurements at once instead of looking at one. And so that's the basic thoughts on flow nets and thinking about how to catch flow, but I'm glad to answer questions about how that applies to various things, or if you got questions about what I shot through there.
Todd, this is Stuart. We have a few email questions here. The first one is, since saline water is very electrically conductive, does this signature ever blank out your images or prevent you from imaging below the salt water?
So most electrical techniques are built to look for conductors like a saline fluid path. When we got into this, trying to figure out a tool for the environmental industry, we were trying to see NAPL bodies, which is the resistor. And so it ends up being that if you look for the resistor, you can actually tune the image to find it. And it helps you then define the subsurface better. So we've looked in that saline mudflat's about as conductive as you're ever going to see. Most of the surface is below 1 ohmmeter, and we could still map out where those fluid flow paths were. So we've got the sensitivity cranked up by about an order of magnitude on the image, and we've been able to see underneath most targets that people say are hard to see.
Great, thanks. Second one is, can you recap how the imaging flow paths can help me on my environmentally impacted sites? I know you talked about an LNAPL site, but thinking about DNAPL sites and other sites like that?
Right, so it depends on what you're, it's taking pictures with an end goal in mind. Are you trying to get to proof that your stuff didn't go somewhere, or are you trying to get to proof that I need to know where the source area really is and whether there's a secondary source, or I need to know if there's a reaction going on that's causing me havoc about where things are mobilizing because microbes are helping move things. Are things below my well? And so it's thinking about where are we at with the current project, where are we trying to get to with a regulatory destination, and then coming up with images to help prove the case about the particular objectives that you have in mind.
Thank you. And then you mentioned the regulators looking at this data. Have they approved this sort of data in terms of making decisions on projects?
So on a regulatory basis, what it ends up being is that the regulation says thou shalt clean up to benzene as this level, or thou shall make DCE do this, or if you do a risk base, we're going to do a different level, but must show that you guys have demonstrated that these things aren't at levels that you need to manage. And the picture, what that tells the regulator isn't that the concentration is a particular level. The biopsy tells them that the same way they've been doing. It tells them that you understand what's happening in 3D and that there's not something sitting between the wells, or that all the things that they're worried about that's sitting out there, they've got, instead of 100 data points to tell them that, no, I think it's okay, you've got 10,000 data points to tell them that, no, it's pretty good, or 100,000 data points, depending how many you're collecting. So it's the ability to fill in the gaps for a regulatory decision so that the regulator and everybody involved in the team can be confident, far more confident than they would be with wells, that the problem has been solved and that you understand what the problem is. Sometimes on like a DNAPL site, the imagery is not something that people enjoy because the D being dense, we see a lot of cases where sites that aren't cleaning up have had stuff move downward. And, so we get a lot of cases where, hey, it's 30 foot or shallower, but we just want to see where we're missing something. We got one well that's still funny, and you demonstrate that actually dropped down 100 feet or something. And that's not a result that people enjoy getting, but it's quite useful if you need to get to an endpoint. And you're never going to get there if you keep thinking it's above 30 foot with a DNAPL and it's actually dropped below that. And for some reason, that distant receptor keeps ending up hot.
Thanks. Great segue to the next question, which is there a depth limitation to this imaging technology?
The deepest resistivity image I know of that's ever been collected is in South Africa, and it was 1,200 kilometers on the surface to look down to the crustal boundary. So it's not a limit of the technology, it's a limit of logistics. You got to be, for the way we set it up, it's 5 times longer than you are deep. So if you want to look down a mile, you just got to have a 5-mile long cable. Most of the work we do is in the top 1,000 feet, and a lot of our environmental stuff is the top couple hundred feet. But you're not limited, you know, like a GPR setup, you might get 10 meters on a good day, but a lot of times you might get a meter. So it's a lot better than a lot of other techniques in terms of depth of investigation.
Next question is, when you're doing these long lines that look deep, how do you deal with road crossings and traffic and things like that logistically?
So it's a call about, number one thing is safety, right? So for safety for the crew and safety for the people driving. So is it something where, you know, on the ultimate level that you close off the road? But if it's, yeah, we can manage the traffic and things, you put in traffic ramps over the cable as it's going, and you basically block off a lane for about 5-10 minutes, get the ramp set up, and then open that one back up. And so then you kind of funnel the traffic around and do those things, but it's traffic ramps to do that. And it works really well, so long as you could do that safely.
Okay, the last question I'm seeing is maybe a good closer anyway. It's if I want to learn more about applying this technology to my site, what's the next step for me?
I call that the wedding photography stage. Is, you know, I'm thinking about having a wedding and I've got these cousins, but 2 of them don't get along. What do I do for taking the pictures? And it's discussing where's the site at in terms of the regulatory context, the issues that are involved, and where you're trying to get to. And then it's a discussion of how would this technology help out with the particular issues you've got. So it's have a little meeting like this, bring up some images of the site, a discussion of what the problems are, a little back and forth, and then, hey, can this really help, and what ways would it help? And that's a really useful discussion to figure out, is this the right tool? Sometimes I tell people, this isn't the tool for you. You want to actually try this maybe, go talk to these people. And it depends on what the project is. But a discussion like this with bringing up some maps, we can walk through what kind of case it is and decide how that would look in terms of applying it in your neighborhood.
Thanks. And we actually have one more technical question come in from our friend Tom Palaya at Jacobs. Have you dabbled in quantifying petroleum natural degradation rates yet? Seems like you can map it, question mark.
The moldy sites are the hardest to map because you actually have signals generated by the more we're finding out about them, the more signals they're providing. So like if you look at a really old refinery, we've got one that is creating tons of methane. And so we've got a couple sites where the gas phase is creating a lot of signals. And then you have the microbes. It depends on which redox phase they're in as to how conductive they are. And then some of them start playing with metals. And so you're looking at a really complicated mold ecology of what that is. And so on the degradation side, it's more of an academic thing of figuring out what you've got versus a regulatory thing of saying, I need to demonstrate levels or below a particular level. But as far as on the academic side, they're making like these cables that go down and they connect different redox zones, and they've got these beautiful 3D structures, and they're really cool critters or sets of critters. So, I mean, they're building all sorts of stuff, and they off gas and they do this crazy stuff. And I figure it's another 20 to 50 years before I could have somebody tell me as a really old guy, this is actually what you were looking at. It's a lot more investment of the microbe people and the people like me taking pictures of their critters and figuring out who's handing what ions to who and which things they're breaking down, and how to utilize that structure to tell us what's going on in the subsurface. But currently it's these areas are moldy. This looks like this kind of reaction has started because we've got some of those handled. But I'm definitively primitive as far as how that life is functioning. I just know that as it goes on, it gets bigger and bigger structures and crazier things going on.
So I think dabbling is perfect choice of words, right, Todd? Because we're definitely dabbling in this arena. We're just learning that there's a lot more to learn the more we learn, and so it goes.
Yeah, and the other great thing I love to do is have two microbiologists chat with me at the same time because they have diametrically opposed views about what things I'm looking at. And so it tells me that they don't have clarity yet either, but there's a lot of hypotheses about how these reactions are all happening.
The industry and our clients seem to be embracing more over time, doing the actual biosamples and learning, how to quantify that. And so we're definitely seeing more activity along those lines on our projects, which is encouraging.
Yeah, and on the regulatory side, it's still fairly variable as to what you're using for proof, at least in my view, of microbial activity, and it depends on what they want to see from them. But the companies that are working on the sampling side are doing a good job of providing sort of an engineering microbe test to say, hey, I want to know if somebody's eating hydrocarbons, and they test for those guys in those colonies to see if that process is happening. And that I think is quite useful for the industry, having the kind of test where you say, I don't care who's doing it, somebody eating my stuff, and can I demonstrate that? And that's been really a nice advance in the last few years.
Well, Todd, it's clear to me you're a seasoned presenter. We're exactly at the bottom of the hour. That's the last of our questions. So I wanted to thank everybody for attending today. We're available for follow-up questions anytime. You'll get a follow-up email with the certificate and so forth. And again, thank you very much. Thank you, Todd. Thank you, John. I'll go ahead and close the webinar.
Thanks, Stuart. Thanks, Todd.
Thanks.